Howdy, everyone. So this is our last mini project about building and analyzing a Bayesian network for VAP prediction. And project is kind of based off of this paper, which allowed for computer-assisted decision support for treatment of infectious diseases in intensive care units and ICUs, basically. And what they did in the paper is they built a Bayesian network that is able to identify what uh, characteristics are most impactful for the VAP problem. And so you have fever and other kinds of symptoms, and putting them together, we see what could be the main factors, right? And that's really what the problem is. Ventilator-assisted pneumonia is what we're diagnosing in ICU patients, and that's pretty difficult. And the symptoms of fever, looking at X-rays, looking at the PO2 score, the FiO2 score, uh, they're kind of non-specific to this pneumonia. And so identifying what the pneumonia models could be with Bayesian networks is pretty impactful for this field. Um, so in our methodology, so we have hard-coded CPTs from medical data, the reference values. There's 300 ICU patients uh, for the probability sampling, and we're inferring the VAP probabilities using the Bayesian inference. And we're evaluating things like accuracy, ROC curve, and area under the curve. So our model looks like this, or in our Python code. We input in our model with these criterions, the fever, X-ray, and the PO2, FiO2 scores. And using this, we're able to basically construct a Bayesian network with a library that we're importing here called scikit-learn, right? So here's a kind of what the head of our data frame looks like here. And we have ones for when we have the condition and zeros if there's not. Uh, and I'll briefly go over just the ROC curve part. So what we see is that our false positive rate and the true positive rate, the area under the curve is 0.95. And I'll go ahead and hand it over to Naima now, who's going to explain the rest of it. Thank you.
Here, we have PGMPY. We have installed this. This is basically the Python library for probabilistic graphical models. Like we are using the Bayesian network, so we have installed this PGMPY. NumPy and PT, we have imported these packages library because for the manipulation and computational task, matplot library .pyplot, we are using this for ROC curve. We have in our task this one. So, and the sklearn matrices, we have used this for the prediction performance. Okay, so here we have defined the graph structure of the Bayesian network. So you can see here VAP, which is ventilator-associated pneumonia. This is the parent of fever, X-ray, and PO2, FiO2. So also VAP influences the likelihood of these three symptoms um, here. And these tables, which is we have defined in the terms of the CPT, conditional probability table. These tables define the probabilities of each node. Here, fever, X-ray, and VO2, FiO2, these are considered as a node, and VAP will be considered as the parent node. So these table define probabilities of each node, and if you see here, the 20% chance a patient has, uh, um, here we have defined here that there is a 20% chance that if the patient has um, ventilator associated pneumonia, okay, which will be one, and 80% chance that patient has um, pneumonia, which is zero. So here variable card, we have defined here too, which means binary term like yes or no, one or zero. So moving further, mm, we can say that if ventilator associated pneumonia is the one, so 75% chances are for the fever in case of this module, this part. And if VAP, which is ventilator associated pneumonia, if its value is zero, then only 25% chances that uh, that the patient has the fever. Same, we have add all these CPTs, and same logic we have applied for the X-ray, for the PO2, FiO2 here bottom, and then we are adding CPTs to model, and we will validate. This will add all the CPTs like CPD, VAP, CPD, fever, and CPD X-ray, CPD PO2, all these CPTs to the model and check um, whether everything is valid. Here we have mentioned the function. This will validate and check whether all the everything is valid and appropriate and consistent also. So moving further, here we have ordered that is simulating synthetic ICU data, and this creates the synthetic data sets, a data set of 300 ICU patient. We have um, we have defined n samples equals to 300, and each patient is assigned a true value, true VAP status based on 20% prevalence. So then, based on the choices, whether the patient has the VAP or not, so we guarantee the symptoms according to probabilities, and at the end, all the data, the results will be framed in the data frame, which is here, data frame, and the four columns. Here you see these four columns which we want in our data frame. These shows each patient VAP status like this, and yeah. Okay, so for this part, we are doing inference and prediction. This initialize the inference engine based on your Bayesian network, and by using this function, which is variable elimination, and we have passed the model, which we have prepared above here. And here you see looping through the, before moving further, I have to explain that this is the list, and looping through the each patient row in the data frame. So for each patient, you are just collecting the um, observed symptoms as evidence. So, and here, so you can see here that this line, which demonstrates the VAP equals to 1 given evidence. This demonstrates that how likely this patient has ventilator associated pneumonia given the symptoms, and this will also store all the predictions to the data frame. But before storing into the data frame, and this predicted probability will be in the list form. And here you see that this predicted probability VAP contains inferred probability of the VAP. And the last line, this demonstrates the binary prediction, where we say that if probability is greater than 0.5, then VAP is considered as positive. Okay, so here the another segment in the part is confusion matrix, and this compares the true VAP labels, like in the form of data frame. We have VAP and data frame of predicted labels. So the output is 2 into 2 matrix. And you see here in the blue roadmap, blue value 169 shows the true negative value for no VAP who actually don't have VAP. So model correctly identified 169 of them as negative. And okay, so here we have the last part to design the Bayesian network structure. And um, network X is the library for the visualization of the graph, and DI graph, which we are using here function. And this is basically converting our Bayesian network into the graphical structure, which is perfect to illustrate the cause and effect relationships. And then we are, adding edges here from the model through this function, edges, adding edges on our Bayesian model. And this, that this edges defines the relationships, which is already defined earlier, like VAP has with the fever, VAP has with the X-ray, and VAP has with the PO2, FiO2. So this is the basic um, Bayesian network structure we have obtained through this um, data set through this project. So that's all about this, and thank you so much.